Number 16. A test charge of positive 2 microcoulombs is placed halfway between a charge of positive 6 microcoulombs and another of positive 4 microcoulombs, separated by 10 centimeters. Letter A. What is the magnitude of the force on the test charge? All right, so on a question like this, it is very important to definitely draw a little picture out. Okay, as the problems get a little more complicated, that's the first thing. All right, so I'm going to give you steps. I might not write them all down, but I definitely suggest you jot some notes. So first step is to just draw a quick picture. All right. Second step is then going to be to focus on the question. So it says, what is the magnitude of the force on the test charge? So what is the test charge? Well, it told us in the beginning, a test charge of positive 2 microcoulombs. All right. So that helps me focus now. In my picture, that my test charge is right here. Okay, it helps me focus on what I need to, I guess, focus on. All right, so I need to find the forces acting on this charge. Okay, now I got a couple of things going on both sides, right? Now here's the beauty, okay? As soon as you identify the charge that you're going to be finding the forces on, you then look at all of the other forces, all of the other charges, which will produce forces, but all of the other charges in this problem as independent of one another. So what do I mean by that? The first thing I want to do, if I want to find the forces acting on the positive 2 microcoulomb charge, is first, randomly, I'm going to choose to talk about, well, what force does this charge apply to my red charge here? What force does the black charge apply to the red? What force does the black charge apply to the red charge? I don't care that this is here. I don't care at all. Literally, it's not even in my line of sight. Okay? So that's my first question that I ask myself. All right? Now, you could have chosen this one to start with. That's fine. But then you would have ignored this. Okay? And let's say I had another one and another one and another one. Who cares? All right? You ignore all of them. You'd work with one at a time. So the first thing I want to do, let's just erase all that. So the first thing I want to do is I want to find the force, okay, on the red charge produced by the black charge. All right, so force, so I'll write that down. Force, actually, let me do this in black. Force produced on red charge produced by the black charge. That's what I'm going to focus on first, okay? And I can call that F. I'll call this F sub. You know what? Let me write numbers here. Let me write. This will be charge number 1. It's a little easier for me to do as I do the formulas. This will be charge number 2, and this will be charge number 3. All right. So the force, basically what I'm doing is I'm trying to find the force between charge number 1 and charge number 2. Okay, so I'll use my little subscripts there. Now, first of all, is this going to be an attractive force or a repulsive force between them? How do you know? Well, this is positive. This is positive. Do likes repel or do they attract? They repel, right? So basically, what's going to happen if I'm just talking about these two charges right now, I know that there's a repulsive force, okay? And I know that the red charge will produce a force in the black charge and will propel it to the left. So really I should draw a red. I'm going to erase it though, but it would be a red vector because I'm thinking, the way I'm thinking about this is I'm saying this would be the force produced on the black charge as a result of the red charge. All right. And then if I want to now flip it, and which is most important in this case, I want to find the force on the red charge, right, produced by the black charge. And that would then be, again, it's repulsive, so they have to be pointing away, right? These things have to be, if they're the same charge, they got to be pointing in opposite directions, right? Remember, if there's a force, there'll be an acceleration, so they're moving away from one another, all right? Now, what's important here is I'm just going to erase this. They would be equal in magnitude, and whatever force we found when we do our calculations, it would be the same for both, all right? But I'm just going to erase this one for now because that's not really of interest, all right? I'm just focusing on the red charge, right? I want to find the net force on the red charge, basically, all right? So now, Once I have this, I got to find the force between the first charge here in black and the second charge here in red. And I know these are charges, and I know they're separated by a certain distance here. I know I'm using my force formula, my electrostatic force formula. I described that one in detail in number 10, so check that one out, all right? So here, if I want to find the force between object number 1 and object number 2, then it will be equal to the electrostatic constant multiplied by the charge of number 1 multiplied by the charge of number 2. You take the absolute value of that product, and then you divide it now by the distance between them squared. So here's the thing. We know the charge of 1. I mean, they gave it to us, positive 6 microcoulombs. They gave us the charge of number 2, right? No, positive 2 microcoulombs. Did they tell us the distance now between these two? Well, no, right? They told us that it's 10 centimeters between the black charge, positive 6, right, and the blue charge that I wrote, positive 4. I mean, that's what it says in this part of the problem, okay? So, but they told us that a test charge is placed halfway between. So now we can easily figure that out, right? So the halfway between point, and how do I want to, I'll do this in green. So the halfway between point here, that means that there's going to be 5 centimeters of distance, right? And actually what I'll do, let me do that. Actually, I'm just going to do it this way. I'm going to raise this up a little bit, and then I'm going to put little subdividers here, okay? And what I'm going to do is I'm going to label each now 5 centimeters. Okay, 5 centimeters. The total's 10, obviously. All right, so now I have everything I need to find the force between number 1 and number 2, right? Which is this vector right here, f sub 1 comma 2, okay? So let's just calculate it. F 1 comma 2 would be equal to the electrostatic constant, 8.99 times 10 to the 9th, multiplied then by the absolute value of the product between the two charges, so that's going to be 6 microcoulombs, so it's just 6 times 10 to the minus 6 coulombs, times then 2, which is the charge of the second one, 2 times 10 to the minus 6 coulombs. Remember, I need it in coulombs. And I did this simple conversion little thing here quick. Check out number 10. I talked about it there. Divided by the radius. Now, you need this in meters, okay? It's centimeters. So it's going to be 0.05. Just move the decimal 2 places to the left and make sure you square it. And now all we have to do is just plug this on into the calculator, all right? So the force between these two charges, which is basically just the force that, we can say the force that the black charge is producing on the red, right? That's part of the force, is now going to be equal to 8.99 times 10 to the 9th, multiplied by 6 times 10 to the minus 6, times 2 times 10 to the minus 6, all divided by now 0.05 squared. And I get about 43.1, so I'll just write the whole answer. 43, I don't know why I wrote it 2. 43.40, actually I do know why, but 43.152, that's why, because 2 was the last number in my head. So this is in terms of newtons. So I know this particular force over here, and remember, if I had to draw the other vector, the force that the red charge is producing on the black charge, it would have been pointing in the opposite direction, and it would have been the same value. This also would have been a value of 43.152 newtons. Okay, so this one is a value of 43.152, and most importantly, since the question's asking me about this is also 43.152, pointing to the right. Now, I know they didn't ask for like directions and stuff. However, whenever you deal with forces, multiple forces, you got to draw a picture. You have to. All right? Well, I mean, you don't have to, but your chances of making a mistake go up significantly if you don't draw the picture. So that's the first. That's not the first step, but that's the first calculation we need. Okay? Now that I fully described the force that the black charge is producing on the red charge, guess what I'm going to do next? I might have already given you a hint by the color I selected. I'm going to now be talking about the force that the blue charge is producing on the red charge. Okay? So the first thing I want to ask so let me write that down. So number 2 here. Force produced on red charge. I'm just reading what I wrote over here. What the heck did I even write? Force produced on red charge produced by black charge. I think I meant to just say force on the red charge produced by the black charge. All right. So sorry if you were wondering what I was talking about, I'm wondering myself as I read it. So, force on the red charge produced by the blue charge now. And I'm going to label that F sub 2, 3. All right, you could write it as F3 too. It honestly doesn't matter. Okay, but it's the force between these. Now, look at the picture, and this is where the thinking comes in. Is the force between now when I'm looking at this picture, by the way, I am not looking at this at all. I know it's there, but I'm literally just pretending it's not. Okay, I don't care that it's there. It's not going to influence how I do this. So basically now what I'm doing in my mind is I'm looking at the red charge and the blue charge, and I don't care that this is here. I don't care that this is here. I don't care about anything else. Okay, literally nothing. So what I now need to do is I now need to think about, is the force of is it a attractive force or is it a repulsive force? Remember, that you gain from the signs. The formula is not going to tell you that. Okay? So since they are same charge, they are the same charge, it's a repulsive force, right? So if I'm looking at the force between the red and the blue, they should move away from one another, correct? And therefore you would have, if you wanted to show the forces on each, you'd have a blue vector pointing to the left there, and then you have a red vector pointing to the right. All right, and the reason why I have it written this way is because if we wanted to think about the force acting on the blue charge, well, the force acting on the blue charge is a result of the red charge, basically. Okay, and also, I mean, it's also a result of the blue charge too, because it does, we take the charge into account, but we can think about it this way. And this force would be identical to then the blue force here and I think about this as the force that the blue charge is producing on the red charge. Okay, now let me just make this one a little neater. Okay, all right, perfect. And I'm going to label that now my F. What is it? 2, 3. Okay, F comma 2, 3. Now, I don't care about this red force. That's not being asked in the question, right? So I'm just going to erase it, but I just do that so that you understand the concept fully. And what I'm going to do too is I'm just going to move this down a little bit so it doesn't get too messy in there. All right. So now what I have to do is I'm focusing on, remember, everything else is not in my head. I am just focusing exclusively on this charge and this charge. Okay. So now let's expand on the force formula. So the force formula, the force of repulsion between charge number 2 and charge number 3 will be equal to the electrostatic constant K multiplied by the product between those two charges in coulombs. We'll take the absolute value, divide it then by the distance between them squared. So let's plug it all in. So F2 comma 3 will be equal to 8.99 times 10 to the 9th. Now multiplied by, I may run out of a little room, so let me just move this over a little bit. Now multiplied by then the absolute value of 4. It doesn't matter which one you call. Actually, you know what I should have done? I apologize, guys, here. What I should be doing here, I should be very consistent. So this should be Q2 and Q3, okay? Not 1 and 2. I don't want you to get confused there. I'm good over here because I had 1 and 2, but this technically I should have a 2, 3 there just so we're very, very consistent. So Q2 was going to be 2 microcoulombs, right? So it's just 2 times 10 to the minus 6, and that you're going to then multiply by now 4 times 10 to the minus 6. Absolute value, they're both positive, so it doesn't really matter. Divided by then their radius between them squared, so it's 5 centimeters, but we need that in meters, so it's 0.05, and don't forget to square that. And now let's calculate it, so F2 comma 3. All right, so now let's take a look. So 8.99 times 10 to the 9th, right? Multiplied now by 2 times 10 to the minus 6, multiplied by 4 times 10 to the minus 6, and then divide that now by 0.05 squared. So I get a value of about 28.768, and that's in terms of newtons. And this kind of does make sense, right? I mean, if you think about it, this force should be less than the force between 1 and 2 because the charge of the blue one is less, right? So that should hopefully make some sense. So now what I should do is let me just erase this black line here. I'm going to make it a little larger, all right, just to show it a little, the proportions a little more appropriately. Okay? So now, How do we find, now I completely described, right, all the forces that are acting on the red charge. There's nothing else in the problem. But imagine I had now a charge up here. What would I do? Well, I'd have to know if it was positive or negative. Let's say if it were negative. Then I would have an additional, and maybe what I should do here is let me do that in red. Okay? Let's say I had another charge here and it were negative. Negative whatever, 4 microcoulombs. Now I have to take a third thing into account. So I would have done the first step, I would have done the second step, and now I would do my third step, literally the same way. I have to think about, is it an attractive force between a positive 2 and a negative 4 or repulsive? It's attractive, right? So now this vector will be pointing directly up to that charge. And then I'm not color coding it since they're both red. But then this force down here would be attracted towards it, right? So the vectors would be pointing together. However, I'm not concerned about the the force on this one, so I'm just going to get rid of it, all right? I'm only concerned about the forces acting on the red. But now look at my picture, right? If I had this extra force, that's fine, but I got to know some other things. I obviously have to know the distance between them, right? And I have to know some angles. But notice, this picture now simply looks like a sum of the forces problem. Right, if I had to now find the resultant force on this, you're thinking about a coordinate system, right? You got a force pointing that way, a force pointing that way, and then another force pointing that way. Find the resultant. Break them all up into their components, right? This literally goes back to the second chapter, all right? And that's why you can't, some of these concepts you definitely got to know like the back of your hand, like vectors and forces and finding resultants, because the concept here is hard enough. Then add on top of that now if the vector stuff is a little shaky. All right, so if the vector stuff is shaky, I suggest you go back and practice that. And also do these problems too, but you got to get that down. All right? So in any case, we don't have that in the problem though, right? So I'm going to just erase it. All right? I'm going to erase it. So let's see if I can just bring this on out without destroying my picture. All right, so let's erase that. Let's erase this. Okay, and now I think you know, though, where we're going, right? Where are we going now? We're going on a long journey together through physics. Hence why I don't say, I'm sorry, you gotta, forgive me, but sometimes I go a little loony when I do a whole bunch of these problems. So I gotta have fun somehow, right? The computer doesn't really talk back to me. And if it started to, I'd start to get a little worried. But in any case, what we now need to do is we now need to find the net force, okay? We now find the net force. Net force on the red charge. Okay? On the red charge. So this one's easy, right? I mean, you got a force pointing to the left, you got a force pointing to the right. You're thinking about how do I add those two together? Obviously, it is a subtraction, right? But if you had a more complex problem, I would suggest you use the component table. I developed that idea way back in the second chapter, I think. All right, so take a look at some of those problems. I think it's the second chapter. It might be the first. I don't remember. But in any case, what I now need to do is I now need to sum the forces, right? So now I'm going to say the sum of the forces, and these are both in the x direction, right? So this should be easy. So the sum of the forces here, what do they equal? Well, I have a positive F 1, 2, and then I'm going to subtract from that because it's pointing to the left, F sub 2, 3. And that's it now, right? So I can finally find the sum of the forces here, and I chose black, sorry. So I can finally find the sum of the forces here by simply taking the black value, right? And what do we get? 43.152 minus now the blue one. If they were pointing in the same direction, what would we have done? Added them, right? And now let's just find this answer. Okay, so here we go. So we got, I'm going to take the exact answers. So this minus then that, 14.384, and I guess 14.4 if we consider then the proper sig fig. Well, there's only, no, each of these only had one sig fig. I'm not going to do 10, though. I'm going to, all right? I mean, I guess technically the answer would be 10. Right? Yeah. Yeah, I mean, but all right. Anyway, sure. So here I'm just gonna round to 3 though. All right, so 14.4. And that's in terms of newtons. That is now the net force. Okay, net force. That's the answer. All right, and then letter B. What is the direction of this force? Is it away or toward the positive 6? Well, we already know this, right? It is away. The net force here is pointing away, right? If I had to take these two vectors, I had my coordinate system here. Let me do it in red. If I had my coordinate system here and I had the black force, right, pointing to the right-handed direction of, this was 40, what was it? 43.152, 43.152. And then I had the blue one pointing to the left, and that was 28.768. The resultant force, the net force, would have been pointing to the right now, right? I'm going to write it just above in red. All right? It would have been pointing to the right, and that's what we found, 14.4 newtons. So it's pointing to the right, and in reference to the positive 6 charge, it is pointing away from that. All right? So if you notice, I took a lot of time on this problem because this is the first problem here in developing the idea of how do we deal with multiple forces on a single point charge when we have multiple point charges. All right? So I definitely want you to understand this concept, replay this video, make sure this makes complete sense. All right? Because the problems are only going to get a little harder from here. All right, and I'm probably going to refer you back to this one. I think it's going to be a good problem that you really understand the nature of how to solve. So guys, thank you very much for tuning in. I appreciate it. If you found any value in this video, if you wouldn't mind giving us a hand by hitting that subscribe button and the like button, telling your classmates, we would greatly appreciate it. All right, we hope you do well, and we'll see you soon. Take care.